All right, I think I hit the right button. Okay. So when it comes to lensometer, we know that it helps us to measure the power of spectacles, right? We can determine information about prism as well, right? And what we're doing with the lensometer is we are actually neutralizing the spectacle lens, right? And we're doing this via the back vertex power, okay? So I just want to kind of draw this out here. So we notice when we're looking at the spectacles in the lensometer here, that the temples are facing away from us, right? And so because they're facing away from us, we have this little guy here, the lens stop, and that is the area which the lensometer is obtaining our data, right? And we use the back vertex of the spectacles to determine the distance prescription, right, of our spectacle lenses. And I think this is a way that they can trip us up on the board exam, where they try to confuse us with front vertex or back vertex. So the back vertex, again, is going to be for our distance Rx, the time in which we're going to spin the spectacles around and get the front vertex is going to be for our add power, right? Another important comment about the lensometer would be we're actually not measuring the true power of the spectacles, okay? Because we're treating the spectacles as a thin lens, okay? So this is another way that they could ask us questions on the exam. And I want to show you what I mean by that here, okay? So let me see if I can press the right buttons here. So let's go ahead and draw a spectacle here, okay? And then we'll go ahead and draw some lights. Okay. Okay, this would be what we're doing with our lensometer conceptually, meaning we have an array of incident light, and we are assuming that this ray of light is refracting right in the center or the middle of the spectacle, right? So this is not the true power. However, this is kind of how we need to think about lensometry, particularly for our board exam, right? So if we wanted to be more specific, to get the true power, we would have to do the following. We'll draw our rays of light. Okay, we'll draw another one here. Go with red. Okay, again, this would be if it was a thick lens. And so if we treated it as a thick lens, we would have to know that the incident light is actually going to refract at, we can call it F1, or the front surface, the front vertex. It's also going to refract again on the back vertex, right? So the rays of light in the thick lens scenario are going to hit twice. And then from that, we would have to determine the principal plane. But I just wanted to kind of briefly show you the difference between the two. And again, for our board exam, we are treating the spectacles as a thin lens. We are not getting the true power, okay, for this reason. So let's talk about the parts of lensometer, right? And we can start out here by seeing us here as the examiner, okay? And we want to have a proper setup when we use the lensometer, right? So first and foremost, what we want to do is we want to calibrate the lensometer, right? So they may ask you questions where they'll give you steps, 1, 2, 3, 4, what are we going to do to have a good outcome here? And so we want to go ahead and set a piece of paper here in the area where the lens stop is, okay? And when we look into the device, we see this reticule, right? And so essentially what we want to do is we want to adjust the ocular here. That way we have a clear image of the reticule, okay? So another thing of note would be this area right here, okay? So this guy right here would represent our lens, okay? And within this system, we have a telescope, okay? And so specifically, we have a Keplerian telescope, okay? Why do we have a Keplerian telescope? Well, specifically because we have a plus lens for the ocular, we have a plus lens for the objective, okay? And a way you can remember this would be perhaps if you were like stargazing and you have a telescope kind of in your hand. That way we can kind of piece this together if they were to draw an arrow at the different areas within the lensometer, okay? In contrast, if we had a Galilean telescope, we would have a minus power for our ocular and a plus for our objective, okay? And so the telescope portion is designed to reduce any type of accommodative effort we may have, excuse me, and any kind of refractive effort we're putting into the device, right? And so when we think about this lens system, let me go ahead and kind of clear everything out here. We also have this fixed lens, okay? And this fixed lens is located right here, okay? And it has a known focal length, and it is located right here where we have our spectacle lens, right? And because we know this relationship, we'll be able to discern the prescription of the spectacles, okay? And so we have a light in the way back of the device, okay? And we also have something called the target, right? And the target we can have right here. And the target we can adjust back and forth, okay? Via this guy down here, the power drum, okay? And what we're doing, in effect, is we want to make sure the reticule, which is located within the Keplerian telescope, is in line with our target here, okay? And then we're able to eventually have parallel rays of light, which are leaving the columnar area down here, okay? They go through the telescope, and we're able to determine the prescription, okay? And again, we are actually neutralizing the spectacle, okay? Another comment to make would be an automated lensometer works a little bit different, right? So in an automated lensometer, it doesn't neutralize the lens. However, it instead just measures the deflection of light rays, okay? So let's go ahead and look within the lensometer here, and we can see our reticule. Okay, we can also see our target. So on this slide, I just really want to highlight the prism that we have within this lower area here, okay? And so we always want to know that the relationship between the target and the center reticule, and we can kind of draw these circles here within the reticule, that will let us know the direction of the prism and the amount. So in the example below, we can see that the target is above the center of the reticule, or right here, it is above, okay? And for that reason, because it is above, we know we have base up prism, okay? And another comment to make here would be the innermost circle here is going to be about half a prism diopter, okay, in terms of the amounts of prism. And every other circle is going to be representative of one prism diopter. So in the case below, I would argue the patient has about a diopter, a base up prism, okay? So let's go ahead and do some example problems here. I would say, first and foremost, right, we want to determine which eye we're working with here. We have the OT, the right eye, and we can go ahead and draw out the reticule here, okay? And the first thing we notice is the targets, okay? Remember those green lines, they are located to the left of the center of the reticule. What does that tell us? That lets us know that we're working with base out prism, okay? It doesn't look like it's going above or below the center of the target, okay? Or the reticule rather. It's just in the base out direction. And if we count over, okay, we have the very center of the target there, about, let's see, 1 and 2. Okay, over. So it's about 2 prism diopters of base out. Okay, so another example here. Now we have a couple things going on, right? So we're still working with the right eye. Okay, we can go ahead and draw out our little reticule here. However, now the target, it's not only a little bit above the center of the reticule, but it's also a little bit away or in a horizontal direction compared to the center of the reticule, right? So we can go ahead and count. We can choose either vertical or horizontal, whatever you prefer to do, not a big deal. But let's go ahead and let's do the vertical first. So if we count here, let's start like 1, 2, and 3 in relation to the target here. It looks to me that we have 1, 2, about between 2 and 3. So I would say about here is where we have the target. So about 2.5 prism diopters of base up, okay? And then we also can see that this kind of middle portion here of the target is actually right on the edge here of this innermost circle. And remember, we said this innermost circle here of the reticule represents about a half a prism diopter, right? So, and because it is to the left of the center, it is base out, right? So 2.5 base up and a half base out. And perhaps on the exam, they'll just show you this image of the relationship between the target and the reticule, just to make sure that you know how to use it properly, right? So now I'd like to go ahead and discuss what's called the Shiner principle, okay? And the Shiner principle was identified by a gentleman named Chris Shiner, right? And this was 400 years ago. It relies on what is called the double pinhole aperture system. And it is a way in which we can measure the spherical refractive error, okay? And it's one of the basic principles that we use within the autorefractor, okay? And we know the autorefractor projects infrared light and it gathers measurements from the way this light is reflected back from the fundus. So within this double pinhole aperture system, I'd like to review conceptually what we're achieving here, okay? So these circles I have here that I'm filling in with the green, those would represent your pinholes. So in the case of an emmetrope, if we don't have this system, okay, they are able to appreciate a single dot, okay? When we give the emmetrope the double pinhole aperture system width, okay, they still see a single image on the retina, a single dot, okay? Now, when we have an emmetrope, okay, and we show them 2 pinholes in front of the eye, they perceive diplopia, okay? Now, certainly if it's in the myope, we have the image crossing anterior to the retina and then projecting backwards. And in the case of a hyperope, it projects behind the retina, right? So if they were to ask you a question on the board exam, we know that it is this double pinhole aperture system within the Shiner principle that is responsible for one of the ways we can determine spherical refractive error, okay? And we also know that considerations in our autorefractor would be poor fixation for the patient and any kind of instrument-induced myopia if the patient is squinting quite a bit, kind of throwing off our results. Let's go ahead and review the keratometer. Now, these are probably collecting dust in our offices, right? They actually measure the anterior 2 to 3 millimeters of the central cornea, right? So we can determine the refracting power of this area. Now, how it achieves this is we have some reflected Myers, okay, within the machine. And we achieve this by using what's called prism doubling, okay? And that's why we have this double image within the keratometer. And the reason we do this is because we want to prevent any type of inaccuracy from involuntary eye movement, okay? And you can use this certainly in patients that are contact lens wearers, as it references in the textbook, any kind of ectasias. But if we're being honest here, we prefer to use corneal topography or tomography, okay? So in corneal topography, we're actually measuring the entire surface of the cornea, right? In comparison to the keratometer, we're only measuring the anterior 2 to 3 millimeters, okay? And so topographers measure the anterior surface of the cornea. It's based on this principle of the Placido disc, okay? And so the Placido disc consists of all these circles, okay? Almost like the reticule, really. And it measures the difference of these reflected mires from the device onto the cornea. And we're able to determine the height of the cornea based on this difference, okay? We can see below here, this would be a patient with a cone, okay? And so when we discuss tomography in comparison to topography, there's some notable differences, okay? So in the case of tomography, okay, we're obtaining the mapping here by using cross-sectional photographs, okay? And by doing so, we're able to obtain images of not only the anterior cornea, the posterior cornea, some pachymetry measurements, a power map, and certainly also we have this Scheimpflug image, okay? And so I wanted to also kind of show you one of the principles that we utilize to obtain these tomography images, and this would be the Scheimpflug principle, okay? So the reason why this works, the reason why we use it is because the cornea has a non-planar shape. Now, if it was a planar shape, okay, all we would have to do is have our image just like this, okay? However, because we have a curve to it, we have our camera set up perpendicular, okay? And we have our light right in the center, okay? So now I'd like to review some different slit lamp examination techniques. So I think the most likely scenario on your board examination would be, they'll show you a pathology, they'll have you identify it, EBMD, right? And then they may also say, well, what type of illumination technique do we utilize to obtain this pathology, right? And in this case, we are talking about sclerotic scatter here, because we see the sclera nice and lit up. Okay, a few other examples that they may show you would be this case below, where we have some retroillumination. We have that nice red reflex from the fundus. And they're talking about fuchs here, looking at the guttae, gutata. And I think another good example here would be using indirect illumination, where we have the light off to the side. And we have the image that we're looking at in the cornea here, about right here, right? And because they are not superimposed, that would be what we would call indirect illumination, okay? So again, if this is our image that we're looking at, we'll just call it that circle there. This will be our light. Because there is a distance between the two, that would be more indirect illumination. Whereas if we have, again, the green circle being the image and this blue circle being our light, now they're superimposed, that would be more consistent with a direct illumination, okay? And this picture, again, taken from the text, we can see, let's say it's a corneal foreign body epithelium we're just viewing right here with the light direct head on. We can appreciate this retroillumination where we have the light bouncing off the back of the eye, coming forward, and it looks like we're viewing something in the stroma of the cornea here. And I think another important consideration here would be in C, where we have sclerotic scatter, just like we had in the previous page, okay? But we're actually using what's called total internal reflection, TIF here. Okay, might be another way they could ask you on the board's exam, describing how you're obtaining the image or how things are working. Okay, and finally, below here we have specular reflection. Okay, and the book likes to cite that it's great for viewing the endothelium of the cornea. Another note here would be it is actually the principle behind specular microscopy. Okay, I think perhaps they could show you an abnormal specular microscopy image consistent with fugues. Let's say cell count is reduced or the shape is off, something like that, and they may ask you, well, what type of a principle or technique is behind this specular microscopy? In which case, you would go ahead and choose the specular reflection. Okay. So now we can go ahead and review some Goldman. Okay. So we know we're applying some force to flatten an area of about 3.06 millimeters of the cornea, right? And we're using a split prism, okay? And that's why we have these two images here, okay? So I think for our board exam, I think the most likely scenario would be, let's say like in B here, they'll say the patient's pressure is 16, okay? And they'll give us some different options here. And they'll say, what is the patient's true pressure, okay? And perhaps they'll give you a number like 20, maybe 16, the same number, maybe 24, and let's say maybe 12, okay? So we know that the answer must be less, okay, than the number given, simply because of the orientation of the Myers of one another, okay? Because the pressure is too high, so we need to go ahead and reduce the pressure, okay? And then we can effectively rule out all these other answer choices here, okay? So I'd like to review some auxiliary lenses here, okay? And as of note, we know the field of view and the magnification are inversely proportional, right? So a great example, BIO with our 20 diopter condensing lens, we have pretty good field of view, but a lower mag, right? In comparison, when we have our 78 or our 90, our mag is pretty darn good, but we kind of give up some field of view. And so I think the Goldman 3 mirror would be the area we need to kind of focus on for our board exam. And so within the Goldman 3 mirror, as you know, we have several mirrors, okay? And these mirrors have different angles, okay? And so let's go ahead and draw out these mirrors in relation to the angles. So when we look here, our 60-degree mirror is going to allow us to see the anterior chamber, okay? Our 66-degree mirror is going to allow us to see the P, the periphery, right? And finally, our 76-degree mirror is going to allow us to see the mid-P, the mid-periphery, right? And so how can they ask us about this on the board exam? So I think if they gave you a scenario, let's say they gave you like a 70-year-old white male complaining of unilateral, gradual, painless vision loss. They have known vasculopathic risk factors, known carotid occlusive disease, and perhaps they'll show you an image here of some mid-peripheral hemes, right? It'll just be a little bit posterior to the vortex veins. And then they'll also show you perhaps an image of some neovascularization within the anterior chamber angle, right? And they'll ask you, which mirror are you going to use to view each image, right? And so we know that if we are shown the mid-peripheral hemes, okay, we're going to be using the 76-degree mirror, right? If we want to view the neo in the AC, we're going to be using the 60-degree mirror, right? And I don't think the best strategy would be to memorize the numbers, right? But if you can kind of know the relationship, knowing that the lower the number, the more anterior we can see, the higher the number, the more posterior that we can see within the eye, I think that would probably be our best strategy. I think another way in which they could ask us questions regarding gonioscopy would be the shape of the mirror, right? And so here we have kind of the thumbnail, apical, apical, however you want to say it, mirror. A way that I came up with to remember it would be A for apical, anterior chamber, okay? A way that we can think about the equatorial mirror here, which allows us to see the mid-P would be TV, right? So we can think about it like trapezoid here, and then vortex veins, perhaps, like just posterior to the vortex veins, we can think, right? And finally, we have the last one here. Oops, I put that in green as well. Let me clear that here. So it's perhaps a little bit easier on the eyes. Okay. And our rectangular mirror is going to be in the periphery, right? So we can think RP, perhaps, like retinitis pigmentosa, maybe. Thinking about those bony spicules way out there, okay? So now let's go ahead and review direct ophthalmoscopy, okay? This is another little tool that probably collects dust, but conceptually, we spend a decent amount of time within the book, so I think it's important to know this for our board exam. So we know off the bat with our direct ophthalmoscope, it provides us a field of view of about 7 degrees, okay? And the magnification it gives us is about 15x, okay? So in the scenario where we as the clinician are emmetropic, we're not accommodating, and our patient is also emmetropic, they're not accommodating, the image which is viewed is actually conjugate to our retina, okay? So I want to go ahead and review the clinical scenario in the book, or the question in the book regarding the optic nerve head size, okay? So specifically, the book asks us, is a myope's optic nerve head larger? Is it the same size, or is it smaller than an emmetrope, okay? So I'd like to do the following, okay? So let me go ahead and draw something off to the side here. E for emmetrope, okay? We'll go M for myope. And then down here, we'll go H for hyperope, okay? And so in the case of a myope, we know they have too much power, right? Their eye is too strong. Let's say they have plus 70 diopters, okay? So because they have too much power, we will represent them as a plus within this system, okay? The patient is a plus, all right? Now with the direct ophthalmoscope, as we know, we have this dial, this wheel within the device, and in order to correct for our uncorrected myope, we need to put in minus prescription into the direct ophthalmoscope, okay? And we will treat, actually, let me redraw this here, that way it's closer to the direct ophthalmoscope. Put it right here, okay? That's a minus. And so we will treat the direct ophthalmoscope as the ocular, okay? Oops, sorry about that, guys. And we will treat our patient as the objective, okay? So in effect, what we have created is actually a telescope, okay? A telescope. What type of telescope? Now we have a Galilean telescope, okay? Remember earlier in the lensometer, we have a Keplerian telescope. Why is it Keplerian? Because we have a plus lens in the objective and the ocular. Now with the direct ophthalmoscope, having an uncorrected myope, and we as the examiner are emmetropic, we have a Galilean telescope because we have a minus lens as the ocular, and we have a plus lens as the objective, okay? And so the optic nerve head is actually larger in the uncorrected myope. There's different ways to think about this. I like to think about it like they just have too much power, therefore it's magnified. Okay. Now let's go ahead and draw out the case of an uncorrected hyperope. Okay. All right, great. So now in the case of an uncorrected hyperope, they have a weaker eye, right? A smaller eye. They don't have enough prescription, okay? And so because they don't have enough prescription, we can treat them like they're a minus, okay? And again, our patient here is the objective. They are the minus, okay? And with respect to our direct ophthalmoscope, okay, in order to compensate for this, we have to dial in plus, right? We have to dial in plus into the direct ophthalmoscope. And we still have created a telescope here, but now, okay, in the case of this uncorrected hyperope, and we as the examiner are emmetropic, we have a reverse Galilean telescope. Why is it reverse? It's reversed because now, instead of having a minus prescription or a minus lens being in the ocular, we have a plus. And instead of having a plus lens as the objective, we have a minus, right? So this is one of the ways which they can kind of trick you on the exam, whether it's reverse Galilean or Galilean, but at least we've kind of drawn it out here and we can better understand these principles. So now we're shifting to chapter 1. Okay.
Can I ask a quick question?
Sure.
So with the uncorrected hyperope, this is Julia. I understand that it's like a nice, like it's a good way to think about it, but in reality, isn't it a reverse Keplerian because the actual lens is still a plus lens? Like, would they ask us about that? Because that lens, the eye lens is still plus. It's just less plus.
Yes, no, that's a great point, right? I think realistically on the exam, I think that they're not going to be that specific.
Okay, it's just a good way to think about it to know the size.
Correct.
Okay.
Like I think this is in the very end of chapter 8 where it kind of reviews one of these questions. And I think, yes, it's more of a way to think about the size rather than, but that's a great point that you brought up.
Okay, so that nerve would be more minified in the uncorrected hyperope.
Yes.
Okay.
I didn't explicitly say that. Or yes, yeah, I think that's a fair way of describing it.
Okay, thanks.
Sure. And so if we go on to our aberrations, let's see if I think I'm stuck on the slide there. Oh, here we go. Great. Okay. So aberrations are essentially imperfections, right? So when light leaves an object and forms the image of that object, not all the light from the object makes it to the image, if that makes sense, right? So we have less detail from the original object inherently, okay? And so I want to first review what paraxial rays are before we get into aberrations, right? So paraxial rays are the rays that form near the optical axis, right? Near the optical axis of the lens. And it's only a few millimeters or less, right? They give us information regarding the image location, okay, as we have right here. Also the image size and the orientation, okay? Now the rays located outside of the paraxial region, also known as the non-paraxial rays, or peripheral rays, those are the rays that cause these aberrations, okay? And in the case of non-paraxial rays, this lets us know the image quality, the brightness, and also the depth of focus. And in this case here, this would be an example of a spherical aberration. We can see that there's a difference between the image point and where the aberrations converge. And this is a hot topic, right, with like the UAD eye drops in terms of the depth of focus, the new pilocarpine eye drops, how it increases that, right? And we can see below here kind of what happens in that scenario where let's say in night myopia, where the eye gets a little bit bigger, and now we have this aberration created where the image or the light is going anterior to our macula, right? And then certainly when we have a smaller pupil here, and then we have a better region within the retina, okay? Now, when we talk about our wavefront aberrations, it's important to know that we are not talking about the wave nature of light, meaning we're not talking or describing waves as a particle or as a wave as we do in physical optics. We're simply talking about time, okay? So in wavefront aberrations, okay, we are assuming that all the light that enters in our system gets at the point at the same time. And the point that I'm referencing is called this reference sphere, okay? And the reference sphere is drawn in relation to where our image will form, right? But we know in real life, this doesn't actually occur, right? So because light does not reach the reference sphere at the same time, we have a series of aberrations, right? And we describe them as wavefront aberrations, okay? And now the difference between, you can see these red lines here, and the reference sphere will kind of further describe the aberrations. Now we can also review chromatic aberrations. When we think about chromatic aberrations, we think about color, right? And we know that depending on the color, it's going to bend differently within our lens, okay? And so even though, at least within the portion that we're covering, the portion of the chapter we're covering this morning doesn't explicitly cover it, we know clinically, if we have a patient, let's say they have a high RX and they're polycarb, and they're commenting that there's all these fringes of colors in the periphery of the lens, it is chromatic aberrations that they're experiencing, right? If they were to give this on the boards. And we may suggest the patient try a Trivex lens as an alternative. We also know that CR39 and crown glass have the least amount of chromatic aberrations. However, they have several issues in it of themselves, right? Okay. And so there's also a page or so within the text that references what are called Zernike polynomials, right? And at first glance, it looks pretty intimidating, right? But if we break it down, I think we can have a successful outcome. So Zernike polynomials are a way to describe aberrations, okay? And I want to break down the different variables that we have within this. Just in case they were to show you an example of this on the board exam. So the Z, which we have here, is consistent in each one of these aberrations, okay? So we don't really have to pay attention to the Z, all right? Now, let's see here. Let's start with the Y, the denominator, right? So the Y, the denominator, that's gonna tell us which order of aberration that we are looking at, okay? So we can draw it out 1, 2, 3, 4, and 5. Sorry about my bad handwriting there. And another comment to make would be orders 0 to 2 are lower order aberrations, right? In contrast, once we reach orders 3 and above, these are known as higher order aberrations, okay? So perhaps they'll show you one of these and you'll just have to know, looking at the denominator, that let's say if it's a 4, it's a higher order aberration. Perhaps if they show you like one of these guys here, it's a lower order aberration. And again, we're looking at the denominator to determine which order we're working with, okay? So let me kind of clean this up a little bit here. Okay. So now let's talk about the numerator, right? This x variable here. So the numerator, excuse me, tells us the number of principal meridians that are impacted by the said aberration, okay? And so when we look at this first one here, we have 0 in the denominator, again, giving us the 0 order, okay? And in the numerator, we have 0 as well. That tells us that all meridians are impacted equally, almost like a spherical lens, you can think about it, right? Here's another example where we have 0 in the numerator, okay? So all meridians in this aberration are impacted equally, okay? And that is in the second order when we look at the denominator. Here's another example where we have 0 in the numerator. Again, all the meridians are impacted the same, okay? So another comment to make about this numerator here would be sometimes we have a plus sign, sometimes we have a minus sign, okay? What does this mean? Okay, so when we have a minus sign in our numerator, okay, this tells us that the aberration has a propensity for vertical tilt, okay? When we have a plus sign, okay, this tells us that the aberration has a propensity for horizontal tilt, okay? So let's just kind of grab a few here. So this one right here, for example, we have a -4, okay? And that tells us that in this aberration, it has a tendency to tilt vertically, right? Let's take another example. So how about this one here? So let's look at the denominator first, right? It's a 2, so we know we're in the second order of aberration, which is a lower order aberration, right? Again, 3 and above is going to be a higher order aberration, okay? And we also look at the numerator, and it's a plus sign, right? So because it's a plus, we know it has a tendency to tilt horizontally, okay? I have a link down here at the bottom if you're interested in reading up on this. I found it to be quite helpful in my preparation. Now, I'd like to end here on astigmatism lenses here. Okay. Go ahead, question? No? Okay. So I think this is a very testable area as well within the chapter, because we want to remember that in the case of the horizontal meridian of an astigmatism lens, okay, it's actually going to form a vertical image or vertical foci line, right? In contrast, when we have the vertical meridian of the astigmatism lens, it's going to form a horizontal image. So they could ask you the relationship between the two. Question? No? Okay. And so I think that if we wanted to extend this even further, we can talk about this circle of least confusion, right? And this is going to be the area where we have the spherical equivalence, okay? There's different ways that we can obtain that information, but we want to know that when we find the circle of least confusion, it is expressed in diopters, okay? Not in distance, okay? And another point to make here, to backtrack, would be in the case of this, let's call this F1, okay? We'll call this one F2, okay? The reason why this first F1 is closer to the lens compared to F2 is because it's a stronger prescription, right? It's going to bend light more, right? And we can kind of write this out, but another comment to make would be the book references that this circle of least confusion, the spherical equivalent, is actually closer to the F1 than it is F2, okay? And the reason this is because you think, well, why isn't it smack dab in the middle, okay? It's because we express it in diopters, okay? If you were to express it in a distance measurement and break it down, it would actually be closer distance-wise to F1 than it would be to F2, okay? So I think I'm ending a little bit early this morning.